Hi, my name is Zeke Ravenscraft. I'm a high school senior at Drew Charter School in Atlanta, Georgia, and I spent the last summer analyzing solar flare data for an upcoming mission. My mentor is Dr. Amy Weinberger, a rocket scientist at NASA. She is proposing an instrument called DAISY, which will launch in 2033 and take images of solar flares. My project is to simulate planning which parts of the sun DAISY will look at on each day. The goal of DAISY is to help us study solar flares in greater detail. We don't yet know what causes solar flares. DAISY will give us valuable data that will bring us closer to understanding them. And DAISY stands for Dynamic Atmosphere Imaging Spectrograph Investigation. The solar flare is an eruption of electromagnetic radiation from the sun. And here's a picture of one happening in extreme ultraviolet light, which is a shorter wavelength than the light we can see. Solar flares are classified by their intensity, which is their energy per the area per time. Flare intensity is written as a class, A, B, C, M, or X, and a number between 1 and 9.9. Each class represents an order of magnitude. For example, an M1.8 flare is 10 times the intensity of a C1.8 flare. On this X-ray flux chart, you can see a solar flare is happening when it peaks above a certain threshold, which is shown on the right. Solar flares happen in active regions, which are the bright, loopy areas on the sun. Active regions, or ARs for short, are temporary regions on the sun characterized by high magnetic activity. Each AR is given a number when it comes into view. When it disappears from view, the number is no longer used. And because the surface of the sun is always changing, ARs can split or merge. This can cause multiple numbers to be close together. So how do solar flares affect us? Well, large solar flares can disrupt high-frequency radio communications, harm satellites, endanger astronauts, and damage power grids. Learning more about solar flares will help us avoid these negative effects. The proposed instrument, DAISY, has a limited field of view and no real-time communication with Earth. DAISY can only observe one part of the sun each day, and this area has to be selected manually on the previous weekday. So the question is, if on every day DAISY observes the active region that had the most flares on the previous weekday, how many flares will it catch over time, and how many will it miss? In addition, what will be the size of the flares it catches and misses? And in this image, one of the active regions is circled. The flare happening inside the circle would be caught, while that's the target. The ones outside would be missed. My project is to simulate planning for DAISY by choosing target active regions using real flare data from 2022 and the method I just described. I'm looking at data from 2022 because the sun goes through 11-year cycles of high and low activity. Because 2022 is 11 years before the launch date of 2033, it's similar in activity levels. So at the beginning, I was given a spreadsheet of every flare that occurred in 2022 and had a class of C or higher. This included each flare's start, peak, and end date and times, and their intensity. For each flare on a particular day, I use helioviewer.org and solarmonitor.org to see which AR the flare originated from. Next, I enter the AR number on the spreadsheet. After this is done for every flare on a particular day, the active region with the most flares on that day is selected as the target for the next day, or on Friday for the next 3 days. If the previous weekday had no flares or tie, I choose the larger or more intense flare as the current day's target. As a shortcut, I added a column to the spreadsheet, which automatically generated URLs for each flare on HelioViewer. So instead of typing or pasting the date and time on the HelioViewer website, I could simply click a link and view the right solar flare. I also added a column to show whether or not the flare's AR matched the target AR of the previous weekday, showing me which flares were caught. Some flares were very hard to see, but HelioViewer had a different image, which was really useful for making them stand out more. One challenge was that DAISY records more data when it sees a flare than when it doesn't. So to estimate how much data DAISY would collect over time, I needed to know the total duration that it would be observing any flare. However, simply taking the total duration of all observed flares resulted in a number longer than the actual total duration that DAISY was observing the flare, because flares were sometimes observed simultaneously. So to solve this, I used JavaScript to write a custom cheats function, which consolidated the overlapping periods of time. This way, I wasn't counting 2 minutes for every 1 minute that 2 flares were being observed at once. The results were that out of 164 flares, 95 were caught and 65 were missed. 53 hours of flare data were observed and 43 hours were missed. The median duration of caught flares was 17 minutes, and the median duration of missed flares is 19 minutes. The median intensity of caught flares was C1.6, and the median intensity of missed flares is C1.8. On the right is a chart of flare duration in January 2022. The green indicates the amount of time a flare was happening and it was observed, and the red indicates the amount of time a flare was happening but no flare was being observed. So the conclusion is that while it's impossible for DAISY to catch every flare, it was able to observe slightly more flares than it missed. There also was not a large difference between the duration and intensity of flares caught and missed. Future work may include analyzing additional flare data and exploring other metrics to determine the best targeting. One alternative method of measuring success could be to determine each day's optimal target and compare success with that of the actual target. I would like to thank Dr. Amy for mentoring me and introducing me to the topic of solar flares, which I didn't know about before. I would like to thank the DAISY team for their work on the project. I would like to thank my science teacher, Ms. Simmons, who recommended me to N3, and I'd like to thank N3, of course, for making this opportunity available. I'd also like to thank my parents for supporting me whenever I needed assistance. And I'd like to thank HelioViewer, Solar Monitor, and all of the data sources they use for making the data easy to access and analyze.